I like this query so much, I put another one inside of it. Welcome to this video on querying SQL Server. My name is Kevin Fiesel. I'm the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, I mentioned the notion of a subquery, a query inside a query. In this video, we'll extend on that idea and see a few different ways to write subqueries. Here's an example of a subquery from our prior video. We can see that inside the exists clause, we define an entirely new query. This particular type of query is known as a correlated subquery because we tie the main query into the subquery. In this case, in the where clause, where there is at least one record in the Chicago population by zip code table whose zip code matches our reference data's zip code. In other words, if I were to copy the subquery out and try to run it, it would fail. It's coupled with the outer query and depends on that outer query for information. By contrast, a non-correlated subquery is one that we could run independently and still expect a result. And here's an example of such a query. Although the examples I've shown so far have the subquery in the exists operator, that's not the only place where we might see it. We can also see subqueries in an in operator or even equality and inequality operators. You can even put subqueries inside the select or join clauses, though I tend to avoid doing that whenever possible as I want to minimize confusion and keep selects and joins simple if I can. Subqueries are a way of defining a query inside of another query. There's another syntactic structure which works really well, the common table expression. Common table expressions always start with a with and appear at the top of a query. The best way to learn is to see some of these in action, so let's get right to it. I want to start us off with a query similar to one you might recall from a prior video. In this query, we're saying to return records from reference data's population by zip code table if there is a row in the Chicago schema's population by zip code table where its year is 2018. If I run this query, I can expect a set of results. This is known as a non-correlated subquery in my exists clause. The reason we call it a non-correlated subquery is that I can take the subquery and run it as is, like we see here. The query worked without referencing any data from the main query, and so there's no correlation to the main query. Non-correlated subqueries are reasonably common, but maybe not as useful as their correlated cousins. Now, moving out of the exists clause, we can use a variety of equality and inequality operators with subqueries. Here's an example where I filter our reference data and only pull back data where the year matches the minimum year in the Chicago dataset, 2018. Once again, this is a non-correlated subquery as I could run it separately. I can also put a subquery into an in clause, and now we're searching for any cases where zip codes match and the Chicago dataset has a year of 2018. And just to prove that it works for inequality statements as well, here's a case where we get all the data prior to 2018 from the reference data table. Now let's switch to a correlated subquery. In this case, I want to check if there's a record in the Chicago population by zip code table matching our reference data's zip code. In this situation, we can see the correlation. We refer to r.zip in the where clause of our subquery, but the table aliased as r doesn't exist in the subquery itself. It's in the main query. That means if we try to run the subquery directly, we'll get a syntax error. This is what we mean by correlation. So now let's do a quick tier list on where subqueries belong. In a where clause, S tier. If you need subqueries, the best place for them to live is the where clause, as that's where people expect to find them. We can include a subquery in a join clause, C tier. Occasionally, it makes sense to include the subquery here, especially if you're performing an outer join and the subquery is a critical part of that outer join. But for the most part, keep the subquery in the where clause where it belongs. In the select clause, D tier, for 3 reasons. Reason the first, it's hard to read. The more subqueries you have, the harder it is for a human to understand what in the wide world of sports you're doing here. Reason the second, having a bunch of subqueries like this is often a sign of thoughtless development. Not always, but often. Reason the third. Let's take this over into SQL Sentry Plan Explorer and run it there. This one query has 5 separate scans of the Chicago table. Yes, it's a small table, this time. But if you try it on a large table, you can end up with a real clunker of a query performance-wise. Okay, wise guy, you might be saying, what do you do instead? Well, here's an alternative. This query returns the same results, yet it doesn't require 5 scans of the table. Granted, not all of your queries will end up compacting down this nicely, but in a shared codebase, you might be surprised how often stuff like this happens. Moving on, let's talk about subqueries in the halving clause. Let's have our base query include the max population per zip code in our reference data. Now we want to find all zip codes whose population is greater than the largest population in the Chicago dataset for the year 2018. It actually turns out that one of these zip codes is in Chicago, indicating that people left on net between 2011 and 2018 in that zip code. As for the subquery in the halving clause, A tier. Respect comes to those who use halving. Now you might be asking, hey, why does where get S tier but halving only gets A tier? The answer to that is, I don't believe in grade inflation. How about the group by clause? No. Hard pass, F tier. Burn this query. You know how bad it is? It is so bad that SQL Server tells you screwed this one up. Get this out of here. All right, now let's do a little palate cleanser after that awful query we just banished. Here's a common table expression, or CTE. I know it's a CTE because it starts with a with clause, it has the name of the virtual table we'll create, has an as clause, and it opens into a query. Common table expressions are a great way of separating data logic into different sections of a query. I can read the CTE, understand a bit more about the data we're going to get, and then move down into the main query where we operate on our common table expression as well as whatever other tables we care about. Here's a slightly more interesting common table expression, one which takes a min year and a max population from the Chicago dataset and then joins two reference data. I could certainly write this as a subquery, but I am partial to keeping data logic broken out into human digestible chunks. We can even chain common table expressions, separating each one with a comma. In this case, I have 2 common table expressions, one for Chicago data, one for reference data. Then I can combine them together. The benefit of doing this is that I performed aggregations on both sides and am working with the post-aggregated results in a way which is easy for a human to understand. In addition to having multiple common table expressions in a chain, we can correlate common table expressions. Now I have my Chicago population. In the second common table expression, I get the year and calculate a 5-number statistical summary using a new function in SQL Server 2022, approximate percentiles. Note that the from clause of Chicago Ag has Chicago data, so I can't run Chicago Ag by itself, but can take advantage of whatever work we did in that common table expression. There's one last thing we can do with common table expressions, and that is performing recursion. Recursion isn't something I've done frequently in T-SQL, but I have done it just often enough to remember the skill. It's one of those once a year type of operations rather than an everyday sort of thing, hopefully. For this table, I'm going to steal an example from Microsoft Learn and hire some employees. Now that I have employees, I want to build up a hierarchy of who reports to whom. The direct reports common table expression gives me an idea of this and shows off the recursion. Recursion in T-SQL requires 3 things: a common table expression with column name specified, like in the example here, a base case, and a union all to the non-base case. Employee level 0 is the base case, people who have no manager. In addition to that, we take employees and join back to direct reports itself to get the employees of those whom we just retrieved. It starts out with our CEO, who has no manager. From there, we grab the one person who reports to the CEO, then the people who report to the VP of Sales, and so on down the chain. In total, we have 4 levels in the company, ranging from the CEO down to marketing specialists and sales representatives. You can also do fun things with recursive common table expressions, like a little bit of ASCII art fanciness. In this case, we indent each level of the food chain a little bit further. When I run the query, we see Ken Sanchez on top, followed by Brian Welker, and then the rest of the employees, each one nestled a bit further in. By the way, if you've worked with recursion before, you might be familiar with Stack Overflows, and not just the site we copy, paste, and pretend we know what we're doing. Having SQL Server crash would be a mighty bad thing. So the SQL Server development team, they automatically kill runaway recursion, and we have some ability to specify what runaway means. If I set the max recursion level to 2 here, we can see that the error that we get when recursion fails to complete. It's just a standard runtime error, and there's no blowing up the machine for us. And that was our tour of subqueries. When it comes to writing subqueries, here's my quick advice. Number 1, need to check existence? Just use exists in a subquery and be happy. Don't try to shoehorn in a common table expression. Number 2, common table expressions conceptually separate queries, making it easier to understand each part in isolation. Number 3, common table expressions aren't necessarily correlated, so there can be performance implications if you're dealing with enormous amounts of data. Here, a correlated subquery might be a better option. Number 4, chained common table expressions tend to be easier to read than subqueries. Now, the clever sort of folks in the back row are probably yelling at their TV right now, "Hey, you forgot the apply operator." No, friends, I did not forget the apply operator, for it is impossible for me to forget such a majestic thing. Instead, I'm saving it for its own video, coming up soon, so stay tuned for that life-changing experience. We'll have links and show notes in the description below, and until we see each other in the next video, take care.